What's up, guys? Happy New Year! In this video, I'm going to be showing you how to use the Nernst equation and when we use it. So, basically, you use the Nernst equation when you have non-standard conditions. And what that means is when you have this thing here. So you have this equation for an electrolytic cell. Wait. It's probably like a galvanic cell or something. But anyways, if you have this, see this, they aren't at the standard condition of 1 mole per liter. So this is when you would use the Nernst equation. And yeah, it looks like there's a lot of information here, but I wrote a lot of extra stuff. So just only focus on what my laser pointer is pointing to. So let's see the question. Consider the following reaction proceeding at 298.15 K. So that's the temperature. So you have this thing and this thing becoming this and this. If the standard reduction potential for copper 2, just this thing here, is 0.340 volts, and the standard reduction potential for aluminum is negative 1.66 volts. What is the cell potential for the cell in volts? So the first step here, so you're given temperature, the volts of the two standard reduction potentials, and this whole equation. So the first step is to find the standard the standard potential for the cell. This circle means it's standard conditions. And what I have down here is I split this reaction in the top, and I got the reduction, the half reactions, because look, copper here becomes copper solid. So copper 2 plus, copper solid. And an aluminum solid becomes aluminum ion. Like that. And how I found a number of electrons is because of the charge. Since the charge of this has to add up to 0, I just added the amount of electrons that would cancel out the charge. So like 2 plus 2 E minus, which is 2 electrons. So they would cancel out. Now, this is the given. But for this one, I actually flipped the sign because this one is actually getting oxidized and not reduced. So this is why. So to get the standard cell potential, I added them up, these two, and you get 2.00 volts. So remember the significant figures. If it's a FRQ, if it's an MCQ, it doesn't matter. Okay, now the next step. So we have this now. And if you look at the bigger picture, we found this part of the Nernst equation. Now we need to find the number of electrons transferred. So you can see over here, just 2 electrons gained by the copper. And there's 3 electrons lost by the aluminum. So how do you know how much electrons were transferred? Okay, so if you look in the top equation here, there is 3 copper. So if you multiply this whole thing by 3, you would see that this is 6 electrons, because there's 3 coppers in the reaction, and 2 electrons are needed for each copper atom. So that's why 3 times 2 is equal to 6. And for aluminum, this is redundant now, but for aluminum, there's 2 aluminums, so and 3 electrons are needed for each aluminum. So 2 times 3 is 6. Okay, and that's how I got 6 electrons transferred. And that will be N. Now we need to find Q, the last thing. We already know what these 3 are, because R is the ideal gas constant, F is Faraday's constant, and T is 298.15 Kelvin. So reaction quotient Q, you would use this reaction here. There's no other reaction to get a reaction quotient from. And remember to ignore the solid, so ignore these. And so you only care about the aqueous stuff. And what I got is this. So the aluminum products over the reactants. And make sure to remember the coefficients, because it is really easy to forget them when you're stressed out. And what do you put in this? So these are the concentrations. So you would put, for aluminum, you would put 0.00790, and for copper, you would put 1.30 in here. So now you have Q. So we found this, N, and Q. And we already know this. So now we can actually just plug all the information we have into the Nernst equation to find the voltage of our non-standard cell. And look at this answer. Look at this answer key. We have 6 electrons transferred. The standard cell potential is 2 volts, and Q is this number. And look, where did they get this number from? Well, it's just this. It's just this number here. But there's like some random algebra stuff happening here because the natural log became a log. So don't worry about that. Just plug all the information in this equation and you should get the same answer, like 2.05. And if you follow sig-fig rules, that's 2.1 volts. Okay. Now I have another problem you should try out. A concentration cell is constructed of iron electrodes at 25 Celsius, and the half cells are 0.0050 and 2.5 molarity in the Fe2 plus ion. What is the voltage in units of volts of the concentration cell? Okay, see, this one, I would say it's harder. And I haven't solved that myself yet. But I have the answer key. So see if you can solve it. Like write out all the equations and stuff that's happening. And solve it. Okay, answer in 3, 2, 1. First, we determine the number of electrons transferred in this reduction of Fe2 plus. So this is what's happening. This Fe2 plus reduction is gain of electrons. So it gains 2 electrons into Fe solid. 2 electrons are transferred, so N equals 2. Then you calculate Q from the given concentrations. Okay. And then note, we have to make sure to put the smaller concentration value in the numerator to ensure that taking the logarithm of Q will produce a negative number, and thus a positive value of E cell. Finally, we place these values of N. Put all this into the Nernst equation, and the standard cell is 0 because the anode and cathode are made of the same material. Look at this. So if you have this equation, if the anode and cathode are the same thing, it'll just be like 0. If the standard reduction potential was like 0.69, it would be like 0.69 minus 0.69. equals 0. So they would cancel out because it's the same thing of both sides. So yeah, I hope this video was good. And I might be a bit rusty because it is winter break. But I'll see you guys next time. I'll be taking like Gen Chem 2 next semester. So I'll have more videos. So see ya.